I need to turn a corner. Now I've finished turning the corner. Oh, now I need to change lanes. Underpants. Greetings, the Astro 30 here yet again, and welcome back to AEL. Now if you're new to this channel, please consider going down below and subscribing. That would help me out a lot. Cheers. Anyway, today we're going to look at another fun experiment with the 555 timer IC. In this case, we're going to be looking about implementing a solid state version of a car indicator flasher. Now, we all know what turn signals are on cars. It's when you flip the stalk on the steering wheel either to the left or to the right. The left side bulbs on the car start flashing to tell you that you're turning left, or conversely, the right ones will flash to tell you and other drivers around you that you're turning right. And it's a simple concept that's been around since, well, the dawn of the car. Not in the early stages of cars, probably like in the late 1900s, probably around about 1920 or something is when indicators started being used. I'm not 100% sure on that, don't quote me on that. Now, the way a standard flasher in a car works is, this is the indicator bulb which is on the outside of the vehicle. There's more of them than that, I've just drawn one for simplicity. And it's marked with an L, which means load or light. Now, the relay flasher unit itself is a thermal flashing unit which uses a heating wire inside of it rather than a coil. And the advantages of this is there's no or very little back EMF when the contacts open again. And all it does is it heats a wire inside the flasher, and the contacts are a bimetallical, and as a kid I always used to call that bimetallical, I don't know why, but that means they will react with heat. So as they're heated, it'll bend. So as it bends, it makes the circuit or the contact, so the light will light up, and because the current flowing through the light is going to be higher than the current flowing through the heater wire will not draw as much current and will start to cool down. As it cools down, so does the bimetallical strip, and it opens again. And then current can then flow through the heater wire again, and the process repeats. And the nichrome wire that they use inside those flashes is calibrated for a certain amount of current that is being drawn on the outside, which is a handy feature because when a globe blows, there's usually two, one at the front, one at the back. There may be a side marker as well, depending on the car. When one of the main globes, which are usually 21 watt, blows, well then the flasher will start flashing faster, which alerts you to let you know that, well, you've got a blown globe. So that's the basics of it, and there's several different types of relay flashes. There's 2-pin, which don't actually have a P connection, which is the panel lights, and I'll cover that a little bit later. There's 3-pin, there's two versions of that. You've got the X connection, which is your battery voltage, the L connection and the P connection. You've also got a version of that where it's a 3-pin with an X, an L, no P, but an E, which is ground. They're more of an electronic flasher rather than a thermal flasher. And then there's a 4-wire one, which has both X, P, L, and E respectively. But we're getting off topic here. We're looking at implementing this as a solid state device using a 555 timer. You could use a 7555 here, which is a seamless version, and that will, when it's idle, draw less current. It's about 7 microamps, I think it is, according to the data sheet. Whereas the standard 555, which is like the NE or the LM 555, the standby current, for want of a better term, is around about 10 mA. So there is a big difference between the two ICs. So this 555 is configured as an OS-stable oscillator. We've got the frequency of oscillation set by these three components here, R1, R2 and C1. I'll get to the rest of the components in a second. Unloaded, this circuit will flash, that is without the bulb connected. This circuit will oscillate at roughly 350 odd milliseconds on, 360 odd milliseconds off. So it's like a tick tock, tick tock, tick tock, which is about the right frequency speed for a flasher relay. Now, pin 3 is connected to this BC547, which is driving our relay with a back EMF diode in the standard configuration. There's nothing to it. Pin 5, the control voltage pin of the 555, is tied to ground via this 10 nanofarad capacitor just to keep the IC stable, and during testing without that capacitor in, I have found that the flash rate is unstable, or the oscillation rate is unstable on this side. It tends to oscillate faster. If this was put in, then it oscillates at the correct speed as it is calculated using an online calculator. Okay. We'll also immediately notice pin 4, which is the reset pin, is not tied high to the VCC as it normally would be. We're actually tying it low via this 4K7 resistor. Now, what is the point of that? Well, forgetting about everything else that's connected to this 4K7, what this does is it prevents this IC from actually oscillating in the first place. Now you may be saying to yourself, well, what's the point of that? Well, flasher relays in cars are ground switched. That means you have the globe down here, it then comes through your indicator stalk on the steering wheel, and then the center of that stalk, which is the common, goes to the flasher circuit on the L connection, and X is connected directly to the battery via the ignition switch and a fuse. So when the switch is on, either left or right, then current will flow through the circuit and flash the bulb. So to mimic that, because we have to have a separate ground for this circuit to work, well, we can't do that. So we put this resistor here on pin 4 to keep this from oscillating. And we get it to start oscillating as soon as the switch is on using this transistor here, which is a BC557, which is connected at the collector to pin 4, and the emitter is connected directly to the VCC line. The base goes through this 1K resistor directly to the L connection, and this diode over here is just a back EMF diode, just to keep nasties off of the circuit from the outside world. So what this transistor actually does is it detects ground, i.e. we've got a ground connection now through the indicator stalk being set to left or right, through the filament of the bulb to ground. So that's our ground path now, or our base voltage now, to turn this transistor on, bringing VCC down to pin 4, which will start the oscillation. However, there is another problem with that. If we were just to have this collector connected directly to pin 4 and this to ground and that going off to the light there, well, effectively now you'll turn this into a buzzer. Because what's happening is, as soon as it detects that ground is applied through this filament, well, it'll try and light the globe up now because the switch will try and close. Therefore, more current is being drawn through the globe than it is through this path, so the transistor will start to turn off again. And then basically what's happening is this transistor is now oscillating, causing the rest of it to oscillate and turn it into a buzzer. We don't want that. So that's what this capacitor here is for. That just allows it to give it enough of a turn on pulse to get it into a 1 cycle frequency of oscillation before it drops out again, still illuminating the bulb bright enough, which is acceptable. It sounds complicated, but it's not. Now, in the intro to this video, I demonstrated the circuit on the breadboard. It was a similar circuit to this, but I had other stuff on there and it didn't work, so the flash rate is slower. However, this one, I'll demonstrate it in just a moment. So, and this 100 nanofarad capacitor across the relay contacts just simply stop any arcing that may occur as the contacts open again, affecting the rest of the circuit here, because there is going to be quite a considerable amount of current draw on the lights on the outside of the vehicle. If they're 21 watts, that's 1.75 amps per bulb. So there's usually two of them. So that's close to 4 amps now, 3.5 amps to 4 amps. So yeah, as these contacts break, they could cause an arc to go across the contacts, which will over time tarnish and damage the contacts, making them not work properly, and could also send spikes back into the rest of the circuit, affecting the oscillator itself. So that's why we've got that. So let's actually look at the breadboard version and see how it works. So here's the breadboard version, and I forgot to mention there that I haven't shown the P connection at the moment. I will go through that a little bit later, but for now I'm just going to demonstrate the high side part of the circuit. Now, ignore most of this stuff up here, it's not relevant. Ignore that trim pot, it doesn't do anything. Most of the circuit is down here. I've got a relay off the screen here. It's just a 12 volt relay that I pulled out of an amplifier. It's a single throw double pole. I've got the contacts wired to the circuit so that we can detect the ground from this side back over here with this transistor. And I've got my power supply set to roughly 12.7 volts, and it is turned on, and it is connected to the load, i.e. the load switch is on. So all I have to do is touch this positive wire to the positive output connection, and it flashes. Now my hand's in the way, so I'll just connect it directly. Actually, I might change to switching the ground side of the circuit, because it's a lot easier to get my hand out of the way. And there it goes, it flashes. But however, you notice initially it goes tick, 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 and then starts oscillating. That's just to do with that transistor and the capacitors charging, and they're, you know, kind of out of sync with each other. So I'm using a tower light bulb which has a 5 watt element and a 21 watt element, and I'm currently connected to the 5 watt element. And we note that the flash rate is pretty fast. Oh, I just farted. Yeah, so what I'll do is my power supply should be okay at this current setting. I had a wire here a moment ago, there it is. I will connect the output of the circuit to the 21 watt side of the globe, and I'll try and face the globe to the camera. Got it. There we go. Notice we've got a much more satisfactory flash rate, and I'm not going to do that too long because it's going to burn my fingers. And there wasn't that initial pulse at the start. I don't know why it's doing that. Seems fine. And currently my power supply is saying we're drawing about an amp. See, works perfectly. Albeit, I reckon those false bounces of the relay is because of the circuit layout is a bit crap. So we can see that when we're drawing more current through the circuit, the flash rate is slower. Now, what I need to know is, if we had two 21 watt globes in parallel with each other as the load, is this going to flash slower? Well, if it is, that means we need to dick around with the component values here. Mainly the second 10 microfarad capacitor, I reckon if we lower it, it will increase the flash rate with the higher load. But that's something I'll explore a little later. But, and it will be before the end of this video. I've just got to go out and buy some actual proper indicator globes because, well, yeah, this is a pain in the ass. Because in order to do this experiment properly, I need 4 of them. I also need 2 pilot lights, which I don't have, but next time down the auto store I'll get some. Anyway, I want to talk now about how cars were traditionally wired for their dash pilot lights. And a short time later, please excuse the crudity of my diagram, I haven't had time to draw it to scale or to paint it. Yes, that's getting a little old. So here's a basic schematic of how cars used to be wired. Some are still wired like this, others are not. We've got the 2 sets of indicator bulbs that are on the outside of the vehicle. We've got a front left, a front right, a rear left and a rear right. Now I'm not going to get into discussing about American vehicles that used to flash the brake light when indicating. That's a whole different topic altogether. These 2 lights here are the panel lights which are on your dashboard, which are underneath the arrow that indicates the direction that you're turning. So we've got the L connection here and the P connection there. The X connection is not shown, but we can assume for all intents and purposes that both this and this are 2 separate switch elements of the same flasher. So the L, or the load, the light connection, comes it down to the column of your steering wheel into the indicator stalk at the common. It can switch either left or right, and center is cancel. So I've drawn it showing it in the left indicating position. Now you would think that this looks pretty simple. Okay, so L is on and these 2 lamps should be flashing because we've got a current path to ground through the lamps through the flasher unit. Seems fine so far. Now we've got a globe connected here and a globe connected here, and the panel connection goes to the center or the common point of both. And you may be thinking, well, how does that work? Well, it's pretty simple. When we're actually switched to the left position, well, effectively this globe, because of the way this is switched, we've got a positive switch here and a positive switch here. This globe is basically out of circuit. It's not doing anything because we've got a positive potential here and a positive potential there and no ground. So the light is not going to illuminate. However, these are flashing, this one's not. But we've also got another path through this globe, through these globes which are currently off, and again using the filaments of the globe, we now have a ground reference to that globe. So as this globe would be like, you know, a 5 watt, I believe they are, maybe 2.5 watts, something, whatever they are, you're looking at no more than about 300 mA of current draw to light this to full brightness. These on the other hand require like close to 1.5 amps to light. So this globe's going to light, but these are not. Isn't that neat? So this one is flashing with these ones. And conversely, if we were now indicating right, this one would be flashing with these ones. But that's confusing. Isn't that the left turning arrow and that's the right turning arrow? No, they reverse them round. That one is the right turning arrow, that one is the left turning arrow. Simple, basic. Question is, why do they do that? Well, I think it's for a simplicity of wiring. Considering behind the dash you've got loads of switching circuits which need to be grounded, and that would mean that there'll be several grounds connected to the body to make that ground connection, especially for lights and stuff. So what they do is they limit the amount of ground connections they have to have underneath the dash, and they just simply run it through the lights to ground, and it works the same way. Safe wiring too. It takes less wires to do it. Simple. Now, going back to the 2-pin flasher units, well, this P connection is not going to exist. And if it's a 3-pin flasher unit with an E connection rather than a P connection, Well, again, this is not being used. And in that instance, this line no longer exists, and this one is grounded, as badly drawn as that is. So this one will flash with these ones, and this one will flash with these ones. So that's about as simple as I can make it. It's kind of neat when you actually look at it. It took a little bit of research and quite a bit of trying to figure out its understanding. Now, I can't attest that all cars are still wired this way. Many different manufacturers of cars do different things. But if the car has a standard 3-pin L, P and X flasher unit, then this would be most likely how it's wired. Anyway, moving on to doing a higher current bulb test with some proper indicator bulbs. I'm going to have to use a bigger power supply because my bench supply won't handle 3 amps of current going all the time. So I'll need to use the 40 amp switching supply just to do this experiment. Plus it's safer, I don't blow anything up. And I'm going to wire a couple of bulbs in this configuration across each side, and we'll just see how the operation works. And I'll leave this bulb on the right hand side cluster and this bulb on the left hand side cluster, so you can actually see that when, say, this set are flashing, this is the one over here flashing and these are not. So let's get going. Well, it's the next day and I've got some globes here. Now, I bought these from a service station last night. I've got some festoon ones. I couldn't find like little panel T10 wedge globes. Probably will do for an experiment. However, connecting wires to it may be a bit more difficult. I've got these wedge style 21 watt globes that you put in your indicator bulbs. Now, my car doesn't actually take these, I don't think. I'm not sure about the front ones, but the rears are just standard bayonet. This lot cost me $30, which is bloody expensive. They're Repco brand, and you probably find they'll be cheaper in Repco, but anyway, these ones I can actually connect my jumper wires, the clip leads, directly to it, so I don't have to solder wires to these globes. And I want to try and avoid doing that if I can, so the globes can be reused. I've only got 2, mainly because they're expensive. I only need 2 really to do the parallel experiment, and I can use one for either side so I can wire up these as I showed in that diagram in the previous clip. So the first thing I'm going to do is just do the parallel test, and the second thing I'm going to do is the full test. So let's get cracking. I'll get that set up, I'll dig out the other power supply and get going. Alright, I've got the PowerTech power supply out and it's set to around about 12.5 volts. Got the 2 globes connected to the circuit now in parallel, so I'll turn the supply on. And just as I thought, doesn't make any difference. So why did a 21 watt globe affect the flash rate and put it to the normal flash rate, whereas the 5 watt globe made it run faster? Most likely due to the current flowing through the filament of the 5 watt globe is different to the 21 watt globe, which affects this transistor circuit over here. So this circuit will not detect when you've got a blown globe. However, that can be expanded by adding, say, a current sense resistor and comparator, etc., to modify the flash rate of the IC so you can tell that you've got a blown globe. However, I've got to now wire this up as if it was in a car. So I'm going to wire these globes as panel lights and have one 21 watt globe connected to the circuit and the other one just connected to ground and nothing else. So let me get that set up. That's going to be interesting with this one. Oh, and just for reference, when both those 21 watt globes are connected and flashing away, we're drawing close to 3.4 amps. Although it's moving around a bit because the meter can't accurately keep up with it. Alright, and a short time later I've got the festoon globes connected as it is drawn on the whiteboard. Now, connecting the clip leads to these are impossible, not without larger clip leads, so I've just soldered a little tag wire off of the end of the festoon globes, It won't hurt them. I can always reuse these. My dome light uses these. I just remove the soldered wires off the end of it. So I've got one set on this side. So we can assume that this is the left indicating relay and that's the right indicating arrow. Similar story over the right hand side. This is the right hand indicator, which is only connected to ground but not connected to the flasher. And this is the left indicating arrow on the dash. So when I power this up, what we should see is we should see this globe flashing, but not this one. We should not see this one flashing, but we should see this one flashing. So that's the theory anyway. How well it works, I don't know. I've got the center point of the relay bridged to the positive, and the light circuit comes off of one side of the relay and the panel lights circuit comes off the other side of the relay. So let's have a look at what we got. And look at that. Just as expected, this one's flashing and this one's not. This main globe is not flashing over here, but this one is. Isn't that special? So it works. However, I've discovered a problem. If I disconnect the globe that's flashing on the left, that was not the right lead, by the way. Let's try that again. That one. It doesn't cancel. That's a problem. And that is most likely because it's detecting ground through the relay circuit. So if I disconnect the globe array, well, it's still ticking away for some unknown reason. It must be detecting ground through the globe here somehow. Yeah, I can see why. This wire goes off to this globe, this wire goes off to this globe, and this wire goes to this globe through to ground. So the whole entire circuit, because this is connected to it, is detecting. So if I disconnect this wire, it stops. So that shouldn't be actually connected directly to the circuit, so I've got the connection wrong for a start. So if I connect it to the globe positive side instead, and then connect this to the circuit, and then connect that back up to the relay, well, it starts flashing okay. That's better. That's how it should work. It was just the way I had it wired. That's fine. So, and the power supply seems happy too. So what I need to do is I now need to simulate switching between the two sets of lights. So I need another one of these fly wires, which I don't have on hand at the moment. Another fly wire later, let's try indicating on the right hand side. Whoops. And there we go. That light's flashing. This one's off, that one's off, and that one's flashing. Neat. Sweet. Just grab my first one. Cool. What happens now if we actually join the two together? Absolutely nothing. The panel lights stop flashing. Well, that would make sense because we're now basically bridging both of them out of circuit. So that's fine. So we have a working concept. Now there is an issue, however, that when the circuit is cancelled, both these panel lights will light up. And it depends on where in the sequence the relay is. See, that one flashed and that one flashed when I just cancelled. So it needs a little bit more modification. But what I might do is I might leave that for another day and come up with a way to counteract that. I'm not sure how at this point. But next thing I want to do before I close this video out is, can we simulate these globes with just LEDs, and will the circuit still operate the same? Because an LED takes a lot less current to light up, so well, it's worth finding out. So let me get a breadboard out. I'll join the cathode ends to the globe end of each array here, and the anodes will be connected as the common point to the P section, and I'll have obviously dropper resistors in there as well. So let me get that set up on another piece of breadboard, and we'll see how that one works. Right, so I've got another bit of breadboard there with two LEDs on either end of it, a common resistor between the two anodes, and the cathodes go off to the ground side of the lights as it was with the festoon globes. Similarly, this one on the right here is going to be the left panel indicator, and this one here on the left is the right. So if I connect, for instance, the left hand side flashing unit, well, that light is lighting up, and so is that one, as it should be. So it does work with LEDs. I don't know if it came out on camera though. Both LEDs lit at the same time when I connected it, and they lit at the same time when I cancelled it. So that is an issue, and it works that way as well. So that's the only issue, is that flashing of the panel lights there when you cancel. So yeah, it would have to be modified slightly in order to overcome that. As I said, I'll do that separately in another video. This one's getting too long, so I'm going to close it out here. The concept works, and works pretty well actually. So I'm going to leave this video here. If you enjoyed it, please remember to go down below, like, comment and subscribe if you haven't done so already. And this is the Astro 30 saying, have a great day. See you in the next one. Thanks for watching.